So now we have seen the case of two different eigenvalues with the same sign, two different eigenvalues with the different signs, and we're left with the case of same eigenvalue. And the same eigenvalue case is split into two subcases. The first case is it's the same eigenvalue, but they're different eigenvectors. In R2, that means we have found an eigenvector xi1 and xi2, both associated to the eigenvalue lambda 1 equal to the eigenvalue lambda 2. So we can again write the same formula for the solution. C1 xi1 exponential of lambda 1t plus C2 xi2 exponential of lambda 2t. And because lambda 1 and lambda 2 are equal, then exponential of lambda 1t is the same as exponential of lambda 2t, so we can take it outside. And now we have exponential of lambda t multiplied C1 xi1 plus C2 xi2. But if we start an initial condition at time 0, then C1 xi1 plus C2 xi2 is exactly our initial condition. So we're multiplying exponential of lambda t by the initial condition. And exponential of lambda t is just a rescaling. If lambda is positive, it means you're pushing away, you're increasing your vector. If lambda is negative, you're decreasing your vector. So what it means is that if you're starting at x0, you're just moving either towards 0 if lambda is negative, or away from 0 if lambda is positive. You have no other directionality in which you're moving. So everything either moves towards 0 if lambda is negative, or away from 0. Notice how this looks like it means that any eigenvector, any vector in this R2 plane is an eigenvector. And that is true, because if you have an eigenvalue of dimension 2, of cardinality 2, with two eigenvectors, that means that any linear combination of the two eigenvectors is also an eigenvector. Think of the identity matrix 2 by 2. That has any two linearly independent vectors are a pair of eigenvectors for the identity matrix. And this is a similar situation. We call this a star point because of the shape it has. We can obviously go back to MATLAB and check it out. Then I would choose, for example, lambda being -5 and 5, -5 for both of them, two different eigenvectors, and I would retrieve something that is exactly straight lines depending on the sign of the eigenvalue, either going straight towards the center or straight away from the center. In a certain sense, this is the easiest situation for plotting. They're only straight lines. Then there is the other case for equal eigenvalues. We have the case of repeated eigenvector. So we have lambda 1 equals to lambda 2, but lambda 1 equals to lambda 2 is associated to only one eigenvector. In this case, we have seen that we can use generalized eigenvectors. So we introduce the eigenpair lambda xi and the generalized eigenvector xi that satisfies either, like both of the equations, either a minus lambda I eta equals xi, or a minus lambda I squared eta equals 0. If you're solving one, you're solving the other. So you shouldn't worry about that. Sometimes one of the two is easier to solve, but it's very much left to you about choosing which one. And if we are in the situation of repeated eigenvector, so only one eigenvector for a repeated eigenvalue, then our solution is of the form C1 e lambda t xi plus C2 block of t e lambda t xi plus exponential of lambda t at eta. So we can take e lambda t out of the parentheses, and then we have e lambda t multiplied by C1 xi plus C2 eta plus C2 t xi. Notice how we had something that is a rescaling, e lambda t, and then something that still depends on time, C1 xi plus C2 eta plus C2 t xi. And C1 psi plus C2 eta is determined. So C1 and C2s in this context are determined by x0. So if we have x0, we start at C1 xi plus C2 eta, and the only thing that moves is the C2 t plus xi. So if we're only concentrating on yt, we're moving along xi applied to x0. So we're moving in this direction in the direction of yt for increasing t. But yt is multiplied by the exponential of lambda t, so that will give us a push either towards 0 or away from 0. E lambda t has a sort of siphon effect if lambda is negative, or a push away effect if lambda is positive. Let's concentrate on the case lambda negative, and remember that lambda positive is just a flip in time. So we're siphoning everything towards 0, but at the beginning we go towards yt. So we start in the direction of yt, and then we're jumped back towards that. So we have this sort of behavior in which things that start on xi stay on xi. They have 0 C2 if you start on xi, while if you are away from the eigenvector xi, you have this swing to go to 0. If you start on the other side, we have again this yt that is bringing you now in the other direction, and then you swing back to 0. So it would look like this. The program I wrote does not consider repeated eigenvectors, so I cannot plot it with MATLAB. But we could do a new program to consider also this situation.